What up? Let's do it. Alright, today we want to talk about inheritance. We're jumping right into it. Actually, no, I lied a little bit. We're going to jump exactly into it. I want to give a little bit of stats first. Oops, wrong one. A little bit of stats first on test 3. Some of y'all like stats. I like stats too. So we have 35 students completed test 3 before the expected deadline. That's out of 59. So not great, but not terrible. Not terrible either. Last time I checked yesterday, it was looking a lot worse than that. So a lot of y'all pulled some late nights and got that done, or you're in different time zones. And another stat I always like to look at: 1, 2, 3, 4, 5, 6, 7. 7 students made a submission but didn't complete the assignment. 7. Let me make sure none of them are TAs. Nope. 7 submitted but didn't finish. That means there's another. The math. 59. 42, 17. So that means there's 17 students out of 59. Let's do that as a percentage. 17 out of 59. 28.8%, about almost 29% of the class did not make a submission before the expected deadline. I honestly do not know what to do with those students. Like what more can I do? Maybe I can say 20 more times to make sure you start early and that summer moves fast, but if they ain't listening to me now, they ain't listening. So those of you who did attempt the assignment did pretty well on it, so I'm happy to see that. That's the one takeaway that I have from that. That most of y'all who did at least show any sign of life out there did complete the assignment. That said, I said this last time, homework, test 1 and test 2, there's a pretty good difficulty spike from those 2 tests to test 3, which you're all aware of right now what that entails. There's, to remove a node from a linked list, you really do have to think about that one a little bit more so than test 1 and 2. And there's also, at least in my opinion, another difficulty spike from test 3 to test 4. Test 4, there's a pretty large volume of just stuff that you have to do. There's a lot of somewhat little things. Bayesian average can be a little trippy, and there's just a lot going on with that assignment. And then I think the difficulty level's off. So if you finish task 4, especially if you finish it before the expected deadline in 2 days, then you're good. You are going to finish this course. As long as you don't give up on me, you're going to do fine. You're going to make it to the end. So this is, in my opinion, the last big challenge. This last one where I really hold my breath on and wait for the stats to come in, wait for the deadline to see how everyone's doing. Hey, Tomato. Hey, how you doing? And yeah, unless there are other stats, you can ask for more stats. I'll pull them up. But Mike is base boosted again. Okay. Thank you for letting me know, Negril. Let me know if that, I made an adjustment, let me know if that's better. Thank you for letting me know. In the 8 a.m. lecture, I lectured for, my mic cut out in the middle, and it went for 25 minutes with no audio at all, and just nobody says anything. Partly because only 2 people were watching, which is its own thing. Mic is better now? Good, thank you. If you ever want more adjustments, let me know. I'll play with the mic settings, make sure we have good audio. There's no reason not to have really good audio. We'll get good audio. I just sometimes gotta change some settings. I just changed the gain, moved the gain down a little bit just now. So if it's not perfect, let me know. We'll get it perfect. But yeah, I lost 25 minutes of audio, and finally someone's like, I think you're muted. I tried everything on my end. And yeah, I was. I don't even know how it happened, how I got muted. It was muted in OBS, just that mic was muted, but I wasn't even touching OBS. It's like it did it on its own. It was weird. But yeah, let's get into it. We want to talk about inheritance today. Because I don't know if my audio is out. I have no idea. So y'all gotta let me know the frustration of that. It's not too big of a deal since I record 2 lectures and you have last semester's lectures and everything. Everybody's going to be able to get the content still. And I did quickly review what I missed, but the frustration of like, I need somebody to show up to live lecture. If everybody relies on the recordings, it's tough. Like in the 11 a.m. in this lecture, a lot of y'all do show up live, so it's a lot better. But in the 8 a.m., I think sometimes I'm lecturing to myself, strictly for the recording. And I'm like, at that point, I could just tell you to watch last semester's. Why am I even doing this if nobody's taking advantage of... Like, the whole reason to lecture live is so you can ask live questions. If nobody's asking live questions and taking advantage of that, and I was doubting why I was spending 2.5 hours of my life doing that for no one, just for no one to even tell me my mic's even out. It was kind of frustrating. Learn with Salim. I took this class 4 years ago in Scala. Man, time flies. Oh my goodness, time flies. It's crazy how fast time's going by. Alright, so what we want to do today is talk about inheritance, and I'm going to motivate this through example. We're going to simulate a little bit of structure of a game that's going to have health potions and weapons, and that's it. And we're going to simulate what happens when a player uses them, and we're going to simulate that just by printing to the screen. We're not going to do much, and we're not going to end up building the full game out of this. In last semester, and in each fall and spring, this will be the case. The project, all the tasks combined for the project to be a game that you build. And in the summer, like, that's just, it's a lot going on with that project. So in the summer, I decided to go back to this ratings and reviews project. So we do actually build a full game in the fall and spring semesters. But here, we're just going to simulate a little bit of functionality. So don't get too excited that we're going to build a whole game in lecture. There's not enough lecture time. So I'm going to start with the health potion class. So I'm going to create a class called health potion, and I want this health potion to do health potion things. So let's have one instance variable, private int. We call it increase in the other examples. Like if you look at the examples here, I never liked that variable name. I don't think it's that descriptive. Potency? Call it potency. Potency, that's how much healing this potion is going to do. So when the player... Oh my God. So when the player consumes this health potion, that's how much they're going to heal. The health potion is going to have a constructor. That's going to take the Alright, so this is going to take 3 things in the constructor. Actually I messed this up. We want 2 more instance variables, so we want to know where our health potions are in the game. So we need double X location and double Y location. Double Y location. So I'm thinking of like a 2D top-down view game where every object in the game is going to have an X and a Y location in this grid. And then we want a constructor that's going to initialize all of our instance variables, which a constructor doesn't have to initialize every instance. Actually, I'm live coding. I can change this example. We have X location, double Y location, and I'm not going to take potency in the constructor parameters. I'll have this dot X location. Like I said last time, I think I do that too often, and it trips students up on the quizzes because they think every instance variable is automatically a constructor parameter. That is not the case. So let me give more examples where that isn't the case. X location, and we'll do this dot potency, and we'll have a fixed potency of, let's say, 15. Just picking a number at random. So there's my constructor, and then I want one method that's going to be public void use. That's going to specify what happens when a player uses a health potion. And for our purposes, I'm going to simulate this with a print statement. Player was healed. This potency HP. Let's whip up a quick main. Just because we haven't seen too many objects being used. So health potion equals new health potion of, let's just spawn at the origin, and then potion.use. So player was healed 15 HP, and if we run this in the debugger, we can see potion has X location, Y location, and potency, and they were initialized to everything that we expected to be initialized to. And the use method, we get this use method being called. Cool. Right? Cool. But we did all this before. We did this last week with classes in Lecture 4. So what are we talking about today? Well, we want to talk about inheritance. So let's rewrite this code, but use inheritance instead of just writing all of the code in one class. So let's set up our inheritance. I'm going to create a second class that I'm going to call game item. And I'm going to split these so we can see them both. I want game item over here though. And I want to create a second class that's going to have some of the functionality of health potion. And I'm going to cut and paste so I don't have to retype all this stuff. I'm going to take the instance variables, value to insert, come on. I definitely hit Control C. X location, Y location, and a constructor. I say and copy. You don't want to just watch me type all this stuff, right? I hope not. Game item. You want to watch me type stuff, just not the same thing over and over. So I'm going to have this game item class that stores all the location information. It's going to have an X location, Y location, and instance variables to store those values, but it's not going to have any of the health potion specific stuff, specifically the potency of the health potion. And what I'm going to do is use this magic little keyword extends, and I'm going to extend the game item class in the health potion class. I'm going to get an error, we'll fix that. But what I'm doing is inheriting from game item. We're using inheritance at this point. So we're going to inherit from game item, and what that gives us is all of the state and behavior of the game item class in the health potion class without having to type that code. So we're going to inherit all of the state from the game item class. The state is all of the instance variables. So this X location, Y location instance variable, we're going to inherit from game item. So they exist in health potion without us having to type it in the health potion class. So health potion has X location, Y location that it inherited from the game item class, and it also has this potency instance variable that it has for itself that's health potion specific. And then we're not going to initialize our X location and Y location here because we're also inheriting all of the behavior from the game item class. In this case, it's only the game item constructor. That's the only thing we're getting right now. But we're inheriting the game item constructor, and we can call that constructor from our health potion constructor. And we're going to do that using the keyword super. So we have two new keywords here, extends and super. We're going to call the game item constructor using the keyword super and give it the X location, Y location that it's expecting. So we get all the state from game item, meaning health potion has potency, X location, and Y location, just like we had with Y location, just as though Y location and X location were pasted in right here. We also get the constructor for game item, just as though the constructor were in this health potion code. It's a little different, it wouldn't be called game item. But we have that constructor, and we're calling that constructor from our health potion constructor, which is a very, very important thing. This is one of the two key things that we want to focus on with inheritance, specifically related to your memory diagrams, your tracing quizzes. Those need two things, two big things that we're looking for. One is superclass constructors, and two is which method is called when a method is called. That's what we'll focus on a little down the road. We haven't quite gotten there yet. But superclass constructors, when you have inheritance like this, when you have a class that extends another class or inherits from another class, this class's superclass, the super constructor, the superclass's constructor is always, 100% of the time is always called when you call this constructor. It's always called. So right here we have super of X location, Y location. We're calling the superclass constructor, and when this wasn't here, we get an error that says you have to call the super constructor. You are obligated to do this. We have to do this. I'll circle back to that. I'll talk about superclass constructors in a second, but I got to get a little vocab out there because I'm already catching myself using it, and I got to put it out there so we know what I'm talking about. So when we have inheritance like this, when we have health potion extending game item in this example, we have a little vocab. We say that game item is the superclass of health potion. That's the one I've already been using because the super keyword just makes me think of that right away. So game item is health potion's superclass. Mike still sounds weird. Makes me think of that right away. So game item. Oh yeah, it does. Let's see. Gains all the way down on the mic itself. I could try changing the mode. Try changing to this. Let's see if that fixes anything. I turn the gain down a little bit on OBS and then change the mic mode. Let's see if that fixes anything. I turn the gain down a little bit on OBS and then change the mic mode. It still sounds kind of crappy. I don't know why it does this. I don't know why this mic is so terrible. I don't know why it does this. I don't know why. Or if it's something other than the mic. It's not a cheap mic. Oh, my fucking dog. Try resetting it. Let's just play with some settings. I don't want to spend too much time on this, but I also want good audio, so just play with some settings. I don't want to spend too much time on this, but I also want good. It's just so frustrating. I don't have any filters. Maybe I should add a filter. Let's do a 3-band equalizer. Maybe that does anything. This is with a 3-band equalizer. Maybe that does anything. This is with a 3-band equalizer. Didn't do anything. I guess I can just turn the gain way down. Wait a minute. Let's try this. Is this better? Hopefully I found something here. Let's try this. Is this better? No, it's not better. God damn it. Let's try this, I guess. I don't think this is going to work, but let's see if this is better. Let's try this, I guess. I don't think this is going to work, but let's see if this is better. Actually, it does sound better. Actually, it does sound better. Let's go with this for a little bit. Let me turn the gain up a little bit again. Let's see if we got it here. I'm going to roll with this for a little bit, and y'all can let me know if this gets better. Let's give it a little bit of a test here. So the game item class is the super class to health potion, and health potion is the subclass to game item. So if I say subclass, that means that I'm talking about a class that, like in relation to game item, it's a class that extends it. Then superclass is a more common one I'll use. Health Potion has game item as its superclass because it extends game item. There's also a parent-child analogy here. So from Health Potion, game item is its parent class, and game item has Health Potion as a child class. And I tend to, just force a habit, I tend to mix these a little bit, where I say that game item is Health Potion's superclass, and Health Potion is game item's child class. So I'll say child class and super class to distinguish between them. And Health Potion is game... Oh, yeah, that audio still sucks. I don't even know what else to try with that. Because sometimes, like, I'll listen back to my lectures, and sometimes they'll be great, sometimes they'll suck. Like, it's just so random, I feel like. It's just so random, I feel like. I think at least for today we'll have to live with it again. It's just so frustrating because, I don't know. Maybe I just gotta spend more money on a mic. I'm using a Blue Yeti. Like it's the one so many people recommend, but some people do say that it's a shitty mic. So I might be jumping on that bandwagon, saying don't buy a Blue Yeti. Don't buy a Blue Yeti. I'm having so many issues with it. I'm on my second one of it too. The first one, I don't have to get into it, but the next mic I get, I just got to spend a little more and get a better one. It's a good intro mic, they always say. I don't know. I feel like I'm not doing anything too advanced. I just want clean audio. But my goddamn microphone on my laptop, the built-in one, is better than this piece of crap. So I don't know. Maybe I got to stream from my laptop. Okay. So we got the vocab out of the way. Let's talk about super again. The superclass constructor call. The superclass constructor is always called. And in this case, the call is explicit. I'm explicitly calling the superclass constructor using the super keyword, and it will be explicit on your quizzes. There's not going to be really a chance for you to miss your superclass constructor call because it's going to be part of the code that you're tracing. You'll have an explicit call to super. You just got to remember what super means. It means go to the superclass and call its constructor. So super is here in place of the superclass. So this is like saying game item, calling the game item constructor. That's what we're doing here. Now, that doesn't have to be... Oh, I have to change this quite a bit. Let's do 0, 0. Actually, let me just delete these. Now, you don't always have to have a super constructor call in your code. It doesn't have to be explicit. If the superclass constructor takes no parameters, then you can have an implicit superclass constructor call. Now the superclass constructor is still called, it absolutely is still being called, but it's not explicitly called. Because when it takes no parameters, Java says, hey, you don't have any choice but to call the superclass constructor because it always has to be called. So I'm just going to call it for you. Like, you don't have to tell me you're calling it because you have to call it. And furthermore, the superclass constructor call has to be the very first thing, so we can make this call explicit if we want. But the super constructor call has to be the very first thing a method does. If we put it not first, it's going to say, yo, that has to be the first thing you do. If that's not the first statement, you're wrong. So since it has to be the first statement, and there's no parameters, so there's no choice in what arguments to give it, Java will say, you know what, you have to call it. Let's just call the superclass constructor without you having to tell me that you're calling the superclass constructor. So it doesn't always have to be explicitly called in your code, but it will always be called. So here we do have parameters, so we have to have our call being explicit because it takes, because we have to specify, we have to tell Java what we want for the arguments. If we don't have this superclass constructor call, it says there's no argument constructor to call, so you have to tell me what you want to do here. What do you want to do with this superclass constructor call? Because you get to choose what the arguments are. So if there is a choice for us to make, the call has to be explicit. Okay, and then we get to run this code, which I did just run it. This prints player was healed 15, but more importantly, I shouldn't say more importantly, but also, let's run the debugger. This is why I ran the debugger before, is when we have our potion object on the heap, that potion still has potency, X location, and Y location. So it still has all three instance variables. Only one of them was declared in the health potion class, and the other two were inherited from the game item class, this X location and Y location. But it still does have X location, Y location. Oh, the audio's getting even worse. What do I gotta try something else, because this is just way too bad. Let me try this. Nothing right there. Let's try this. Test. Give me something right there. Let's try this. Test. Give me something. All I got was it's quieter. What if I do this? Does this even do anything? I feel like the gain on the mic doesn't do anything. If I do this, does this even do anything? I feel like the gain on the mic doesn't do anything. I don't know. That sounds might be better. I mean, it's quieter. I gotta turn this gain up a little bit now. I don't think the gain on the mic did anything at all, though. I think it's all just an illusion. Let's try this one a little bit. So we inherit all the behavior, and we inherit all of the state. Go right here. Okay. And my question to you, and the question you should be having, is why would we do any of this? Why would we use inheritance? Oh god, that's so much worse. Son of a bitch. I don't want to mess with this stuff. Alright, so why would we ever do this? Let me try one thing. This will be the last thing I try, and then I'll just lecture. Then I'll tell you why the hell we're using inheritance. I'm going to try one quick thing. if this don't work, I'm giving up. At least during this lecture, I'll stop messing with it during lecture. Because this isn't what y'all came to see. Jesse messing with mic issues. Not exactly, not exactly helping you with your homework. Not exactly helping you with your homework. Yeah, well, I'm sticking with that. Alright, so why would we ever do this? This seems like a silly thing to do. Why would we do this? Well, because with one class, what we showed in the debugger is that we got the same exact behavior out of the health potion class, except we added a lot of complexity here. We have two classes now. We have this extends. We have to understand how inheritance works. We have a superclass constructor call. We just got a lot going on here that we have to know in order to be able to read this code. So this code got a lot more difficult to write and a lot more difficult to read. We have to look at two different classes just to figure out how one class behaves. So that's kind of silly. The reason we would do this is when we have more classes. So if we have another class, I always call this weapon in the other examples. Since I'm live coding, I'm going to change it to sword. I think that makes a little more sense, a little more concrete. And can I split this again? Ooh, I can. All right. Let's get all these on the screen at once. Let's collapse this. Let's do this. No, we can't quite get everything on the screen, but we'll get close here. A sword is going to have private. I'll make this an int. Attack power. Attack power, which I'm going to hard code to 120. Just making up a number. And it's going to deal that much damage when a sword is used. So if I have the use def void, this isn't Python, public. When you know a bunch of languages, they bleed together sometimes like that. And I'm going to just simulate this by printing to the screen delt this dot attack power damage to whatever you were attacking. And we want to inherit the state and behavior from the game item class. So we're going to do our extends from game item. So game item is going to be the superclass. We're going to get an error because we don't have our superclass constructor call. So we're going to need a constructor call sword, which I'll take x location double x location double. Actually, let's get a little cute with this one. Let's not take any parameters in the constructor. And then we still need our superclass constructor call. And let's just say every sword spawns in at a specific location. Let's say 10, 4.5. Every sword is going to spawn at that specific location. That's your sword spawn location. So you have to navigate to that place in the map if you want to pick up the sword and have and use this sword. And then our attack power is already initialized up here. So we have a fixed attack power, a fixed spawn location, and that's how our sword is going to behave. So this is our sword class, and this is where we get the advantage of inheritance. When we write the sword class, the only thing we're worried about is how swords behave. What does a sword do when a player uses it? Well, it's going to deal damage, and I'm going to say that damage can vary. I can have different types of swords, and the default sword is going to have 120 attack power, but I might have different swords in my game that have different attack power that we would change presumably through getters and setters or another constructor which sets the attack power. And we don't have to worry about any location stuff. So I'm inheriting everything to do with location. What I'm doing is taking anything that's common between all of my items in my game, my swords and health potions, factoring out the common functionality and putting that in the game item class. And then extending game item, so sword and health potion both get any location functionality based on that inheritance. And I can put that functionality just in the game item class, and now health potion, sword, they both get X location, Y location, without having to write that in every class that's going to be an item in my game. Which, that's fine. Every class. Yeah, the audio didn't even change at all. I feel like every setting I'm changing doesn't even make a difference. So, are there any exercises associated with these lectures? Sure, test 4. You want more than test 4? And the other lecture examples, and the examples I'm doing right now. If you're not registered for the class, so this is an actual class at a university. I assume you're not registered in the class. You can go to CSE116.com, and you can find all the homework assignments. So you can find the definition of test 4. You won't be able to submit if you're not registered for the course, but you'll still be able to do the assignment. You just wouldn't be able to get the auto grader running on it. The test 4 is all about this stuff. Okay, so that's fine. We get these 2 instance variables, but like you can cut and paste these instance variables in both classes. That's fine. Not perfect, but fine. But where this really starts benefiting is when we have more functionality in the game item class. When we have, say, a move method, we take some dx, some dy, and we move this object. This dot x location plus equals dx, this dot y location plus equals dy. Now I write this method one time, and now both health potion and sword are inheriting this behavior, inheriting this method from the game item class through inheritance, through this extension. So both health potion and sword now both have a move method. I can do potion.move. That's a perfectly legal thing for me to do because a health potion, this potion of type health potion, has a move method that it inherited from game item. So when I add more movement behavior, any location-based stuff, I'm going to add it to the game item class, and then all my objects, all my classes that extend game item, they're all just going to have that behavior. They're just going to have it. It's going to be part of that class. So this is where the benefit really comes in, because yes, you can keep making the argument that, well, I'm not going to learn inheritance. I'm just going to paste my code like this. I'm going to do this every time, and then have the instance variables and everything. You can do that, but what you'll have is duplicate code that you're maintaining, which is not a good idea. It's not good practice, and the reason for that is that whenever you have to update this method, say you want to add a z-axis here, you're going to add it here and change that code, and then you have to add it here, which, yeah, maybe you'll write the code once and then cut and paste it, but you have to remember to cut and paste it, which is just inviting more errors, more mistakes, and more bugs in your code, because you might forget to update it one place, but do update it in another. So if these methods get out of sync, one of them has a z-axis and one of them doesn't, or you find a bug in a method and you fix it in one place but not in another, it's just more work and more error prone. If you have one copy of the method, then if you have a bug in this method, you're going to fix it, and it automatically propagates to all of the child classes. They just get that fix or that updated code or that additional axis, that z-axis, without having to worry about any of the sword and health potion specific stuff. All that functionality is still there, but if we add a z-axis, we don't even have to go into the health potion and sword classes at all. We can just add the z-axis and, not even let them know that they have a z-axis now. A sword and a health potion, they don't actually care when we're using inheritance because we just add it to the game item class. And with this class the way it is right now, so 2 more things. With this class the way it is now, still you'd be like, yeah, whatever. I'll just cut and paste that code. It's a move method. It's pretty simple. But we might have hundreds of lines of code in the game item class. We might have all of our physics functionality in here, where objects are moving through space and time. They might have gravity applied to them after we add that z-axis. They might bounce off other objects. We might be detecting collisions between other objects based on their hitboxes. We might be doing a lot of stuff in here that we don't have time to do in a single lecture, but we might be doing a lot of stuff in here, and we don't want hundreds of lines of code pasted into each one of these child classes. That's where things really start getting out of hand, and it's when you're debugging some obscure physics engine bug, you don't want to go to each of your classes and update it in all of those classes. You want to maintain that code one time, and that's it. Then you only have to test that code one time. You don't have to test it in the health potion class and the sword class. In task 4, I actually have you do that. You have a song class and a movie class that both extend rateable after you do the setup. And then for the testing, I have you test movie and song separately, which is a pain. Yeah, and you should be thinking, man, I wish I could just test this once and be done with it. That's the idea, is we want to test it once in the super class, and then it's tested. It's done. It works. And all the child classes will just get that method. But if you write the code in each child class without using inheritance, now you have to test each child class individually, and that's a pain. The other thing is we only have 2 game items here, 2 types of game items. But we're going to want more. Like if your game only has swords and health potions, it's not going to be that fun of a game. I mean, maybe you're an expert level designer and you can make that fun. But for the rest of us, we're going to want more game items. We're going to want rocket launchers and bows and arrows and mana potions. We want all kinds of other types of game items. We might have hundreds of classes that extend game item. And at that point, even with a simple move method, I don't want to cut and paste this hundreds of times for every single one of my classes that extends game item. I just want to put this in game item one time, write the code one single time, and then hundreds of different classes inherit that behavior. That's the functionality I want. Okay, and I want using, oh, look at that. Look at me go. I got this set up exactly the way I want it for the memory diagram, so let's jump to a memory diagram. So let's grab the health potion class and the game item class, so the only 2 I'll need for this one. Let's do some tracing. This is the trace we're heading up to. Who's excited? I am. Show toolbar, trash can, all that, because I'll be redoing it. Health potion and game item. We don't need weapon yet. We will grab it later after we add a bunch of functionality to all these. Okay. In the slides I do weapon, so I want to switch it up and do health potion here. Okay, so every Java program starts with, something's weird here. Just because I'm not full screen, I guess. Every Java program starts with main. And we have potion. Equals new health potion. I always put this right away so I don't forget. And that's creating a new, I see the keyword new, so I'm creating a new health potion. Map the constructor. And we get to our, and so far that's object creation. We've done that a ton of times already. But we get to our first new thing with inheritance. Now that we have inheritance, when we put the variables, well, I guess we can get the last thing that we do, that we have done before. We can get this being a reference to the object being created. Health potion. We're creating an object of type health potion, so we have to look for all of the instance variables in the health potion class, and we have potency. But now with inheritance, we have to also look at the superclass to look for all of the instance variables that we inherited. So we're going to go over to the game item class, and we're going to grab all of its instance variables, which is X location and Y location, and our health potion object is going to have all of those variables. So all the variables in the class itself and all the variables in its superclass, we're going to get all of those instance variables. And then we're going to look at the constructor. Don't make the mistake of just putting every instance variable on the stack. We're going to look at the constructor just like every other method call you've ever done since 115. The only exception is we have the keyword this, is we're going to take the parameters and put them on the stack. So potency is never going to make it to the stack, and that's perfectly fine. We're just doing what the code tells us to do, and nowhere in this code does it say put potency on the stack. When I see potency on the stack, if I gave you this as a quiz and I see potency on the stack, I know you're not really understanding how constructors and object construction works and objects on the heap in general. There's some disconnect there because there's nothing in this code that tells you to put potency on the stack. The stack is your parameters. It's not a parameter. Doesn't go on the stack. So X location, Y location got 0, 0, 0, 0. And then we make our super constructor call, our second thing that's different with our object creation with inheritance. Our super constructor call, this is a method call to a constructor. And this gets a little trippy, but we have a game item constructor call where this is still a reference to the object that's being created. And we have two parameters, X location, Y location. That are going to get X location, Y location from this stack frame, 0, 0, and 0, 0. Graduated 2 years ago. I just want to say hi and thanks for everyone. Definitely one of the most memorable classes. Thanks for everything. Memorable classes I took at UB. Oh, thanks you, Janero. Thank you for the kind words. It's always fun to hear that. And then we're going to run the superclass constructor. This dot location, X location equals X location is 0.0. And then this dot Y location equals Y location 0.0. I shouldn't have done 0.0. It's kind of boring seeing that in the trace. And then that's the end of this constructor call. So what we just did was called a constructor without constructing a new object. We're going to have, when we have inheritance like this, we have two constructor calls that are working together to initialize and create one object on the heap. So it's a constructor call that does not correspond to a new object being created. And your keyword there, the literal keyword, is new. When we say new health potion, we're using the keyword new, which is your clue that you're going to hit this button right here and create a new object on the heap. When we call the superclass constructor, we don't see the keyword new. There's no keyword new. That means we're not creating another new object on the heap. We're not hitting this button right here to create a new object. We have a second constructor call that's working together to create that one object. And its job is to initialize X location and Y location in this case. It's doing a partial initialization of that object and then handing off back to the original constructor to initialize the rest. This dot potency equals 15. Then this returns, and just like our other constructor calls, this returns a reference to the object that was created. So two constructor calls to create one single object. So that's the first big thing with tracing code that uses inheritance is superclass constructor calls. They are always, always, always called. I'm going to say this so many times in lecture, I'm going to be absolutely shocked whenever somebody, and I am in the past, whenever somebody messes this up on a quiz, when you forget your super constructor calls, that is an instant fail on the OOP quizzes. If you submit your OOP quiz with everything perfect except you missed a superclass constructor call, easy fail. Like you missed one of the two things we're assessing in a regular graded percentage-based class. That's a 50%. You missed half of the stuff that you needed to know. Especially if you miss it every single time. Then I know you just don't even understand superclass constructor calls. And I say it so many times in lecture, you're going to get sick of me saying it in lecture. But I swear, some students will still make that mistake. And I just assume that they're the students who don't go to lecture, because I don't see how it's possible to go to lecture and miss your superclass constructor calls. I say it way too many times. So don't forget your superclass constructor calls. That's always, always, always called. If you see extends here, you know you're going to have 2 constructor calls, or possibly more if game item extends something else. I won't throw that at you on the quizzes. We don't need to get crazy with things, but I will have cases where there are 2 constructor calls, and you need to remember your superclass constructor call. That will absolutely happen. So I need to know that you know that the superclass constructor is called when you construct your object. And on the quiz, I'm going to make that explicit, like I mentioned earlier, so it's pretty hard to forget. Like if you're tracing through the code, the only way you can miss it is if you just skip this line. Hey guys, I ended up here randomly. What is this lecture about? This is about inheritance. And can anybody give me more context, because this is looking interesting? If you go to CSE, I'll just type it in chat, CSE116.com. This is actually a course taught at UB, the University at Buffalo. So it's taught for that course, but I make it public so people like yourself can, geeky tutorials, so that people like yourself can just wander upon the stream and don't want to be behind closed doors or anything. So anybody who finds value in it is welcome to stumble upon it. But it is part of that course, so if you want to see the syllabus and the assignments and everything else related to the course, CSE116.com. Okay, so then we're ready for the next line, potion.use, and this is the second thing we need to know about inheritance. And specifically, this course is taught in Java. It's a second course in computer science, so there's a lot of basic knowledge that's assumed. And then we're diving into deeper topics like today, inheritance. Last time we did linked lists. Next time we're going to do binary trees. By the way, it's Tuesday, Thursdays, our lecture days. Well, I guess the rest isn't on the syllabus, but Tuesday, Thursdays are lecture days from roughly 8 a.m. to 1:30 p.m. Eastern Standard Time, and there's 2 separate lectures in that time, so I basically cover the same topic twice in 2 different ways. Okay, so potion.use, so we have a call to the use method. It's a non-static method call, so we're going to have this. So basically, if we see a super constructor in a trace, we should create a new object on the heap. If you see the keyword new, you're creating a new object on the heap. When you get to the superclass constructor, you are not creating a new object on the heap. That superclass constructor, so this game item constructor call, was assisting the creation, the construction of this health potion object right here. This health potion object was initially created when we called the health potion constructor. And your trick for that is when you see the keyword new. New means you're clicking this button right here and creating a new object on the heap. But when we got to the superclass constructor, there's no keyword new, so we're not creating another new object. We're not creating a second object. Some students will do some crap like this. I shouldn't say crap, but some misunderstanding like this. They'll create a game item class with X location, Y location. None of that. We don't do that. We don't do that. The game item constructor that's being called here, because super is in place of the super class name, so we're calling this game item constructor right here, and this call. That's the part you do have to remember what that keyword super does. But since we're not using the keyword new, this constructor is assisting in the construction of this health potion. And in this example, that's where its X location and Y location instance variables are being initialized. Okay, so we have use potion.use called from this object right here. This is OX100, and I'm going to go through this. I'm going to explain this, but it's not. It's going to be more relevant in the next example, but I will cover everything you need to know in this example. Is when a method is called, which method is called. And for this, it's going to start off the same exact way as we have with every method call, especially the example last week where there was a party class and a character class, and both classes had the win battle method, and we had to pay attention to the type of the calling object to figure out which method was going to be called. That was motivating this topic right here, is we want to do the same thing. We have OX100 calling the use method. It's not relevant in this example because you literally can't get this wrong. There's one use method, there's one move method. You know which ones are going to be called, but I want to explain why. So when it does get trickier in the next example, we can still go through the correct procedure. So it's being called through OX100, which is of type health potion. So we're going to look in the health potion class for a method named use that takes no parameters. We find it right here, and this is the method that's going to be called. And we get printed to the screen, player was healed. I feel like that's a wrong, healed just feels like the wrong word there, but I think it is right. This dot potency, 15 HP. Method returns, doesn't return to anything, it's a void method, called for side effects. Okay, then moving on, potion.move, easy enough with the first one. We have move called from OX100. And we're going to do the same thing. Oh, we have parameters though. We know what the arguments are, so let's get the arguments down here first. I don't know what the parameters are yet because I don't know what they're called. I got to find the code for the method first. So we're calling this from an object of type health potion. So I'm going to look in the health potion class and look for a method named move, and I don't find it. And then I panic and I go, this code's broken. I'm calling move from a health potion. Health potion doesn't have a move method. Everything's broken, everything sucks. Well, no, this code does work fine. What happens here is we start going through our progressions. So we start at the class. That's how everything starts, is at the class matching the type of the object that called the method. That's how we did it last week. That's how we started doing it this week. But where inheritance kicks in is when we don't find the method that we're calling, when we don't find it in that class. What we do then is we say, okay, it's not in the health potion class. Let's move on to the super class and see if we can find it there. So we're going to move on to the game item class and look for a move method in this class, and then we do find it right here, a move method that takes two doubles. It's right here, and this is the method that's going to be called. So we always start in the child class, and only if we don't find the method we're looking for, then we move on to the super class. We find it here. Our parameters are dx and dy. And then we run the code. This dot x location plus equals dx 1.0. This dot y location plus equals 3.6. This returns, goes back to our main method, which is over, returns, and that's the end of our program. Over, returns. Man, audio's driving me nuts. I don't even know what else to try with the audio. I don't know what else to try during lecture, I should say. There's some other things we can try, but I'm done messing with it during lecture. Oh no, I'm trapped. There we go. Silly things. Okay. Let me double check, make sure I'm not forgetting. I feel like I am forgetting something. Yeah, the object class. So let's get rid of that. We don't need everything on screen all at once right now. So with inheritance, actually every single class that we write does inherit from another class, from exactly one other class. Now health potion obviously inherits from game item, but game item also inherits from something. It extends object. If I can type properly, we'll get it. It extends object. If you do not explicitly extend anything, you implicitly extend the object class. And the warning I get here is, hey, you don't have to tell me that you're extending object. I know you extend object because everything extends object. So I don't actually have to say this at all. Game item already extended object without me having to say anything. And if we go into the object class, actually let's not go into it yet. So the result of this is that every single class in Java extends object either directly or indirectly. So game item extends it directly, and I don't have to be explicit here. I can delete this, and that's the same exact code. Everything's exactly the same. Game item still extends object. In fact, problem set that we wrote for task 1, that extends object. Song extends object. Everything extends object. Every single class you write that doesn't explicitly extend anything. If you explicitly extend something, you no longer extend object. So health potion extends game item. But since game item extends object, health potion still extends object, just indirectly. So health potion gets all the state and behavior of game item, which already has all the state and behavior of object. So health potion through the game item class will get all of the object state and behavior. So the result is every single object in Java, every single class extends object. That means every single object has the state and behavior of the object class. If we peek in here a little bit, I don't want to get bogged down on all the stuff in here, but object has a few things that we used. Equals. So everything has an equals method. This is how we got away with, in our linked list example, how we did dot equals on an object that was a type parameter. We didn't even know the type of that object. But since every single object in Java extends object, and object has an equals method, that means absolutely every object in Java has an equals method. And by default, if you don't change the equals method at all, by default, this is what it'll do. It'll check if the two objects the two references refer to the same object on the heap. So that's why we got that behavior when we talked about dot equals. And also, when we talk about dot equals with strings specifically, if we just use equal with strings, well, that actually is a different example because that is, never mind, that's a different thing. And also toString. Last time we saw toString, we did talk about this, and we did the next thing that we're going to talk about. Actually, no, it's not the next thing. I'm going to stick with this ordering too. Go to this slide just to make sure I don't forget anything. Is the toString method. So we have a toString method as well, which is going to give us that default behavior of toString, which we will actually talk about this a little more later in the lecture. But we get this default toString behavior, which for our purposes right now does exist in every single class. That's why we can convert anything in Java to a string. We can call toString on every single object because it's part of the object class. So absolutely everything has a toString method. So toString equals, and a few other methods. You can see the other methods in here. Methods that we're not going to use in 116. The ones relevant to us in 116 are toString and equals. So those exist in every single class through inheritance. That's why those methods just magically exist. That's why we can print a health potion to the screen, and that code just works. Okay. And in my brain, I got to shift gears a little bit because it's the transition between Monday and Wednesday in the regular semester. But really, it's just rolling through with inheritance. So we want. So what we can do is in our game item class, I have this use method in health potion, and I have a use method in sword. And let's get sword back on screen, even though it's going to get a little cluttered here. Want this over here. Get rid of this. Get rid of object. So sword and health potion both have a use method. So what I can do is put this use method right here, let's just do some setup here. Void use, and now both sword and health potion are going to inherit this use method. And let's just print out item use, just to simulate that that method was called, just so we'll know that method was called. And then in our sword and health potion classes, we inherit that method. Which way do I want to do this? Does it really matter? I mean, it doesn't matter, but let's get rid of this one. Doesn't matter. It's a meaningless decision, but I sit here and decide too long on it. So when we inherit that behavior. So if the sword class extends game item, sword gets this use method, and it gets the move method still. But we get the use method inherited in the sword class. But what happens, and we inherit all the state and behavior, all the instance variables, all the methods. So what happens when we don't want exactly the method that we inherited? Well, that's where we can override the method. And I'm going to talk about this annotation a bit, but we can override the inherited method that we get. So we inherited game item from use, we inherited use from game item, and we say we don't want that use method. Replace the inherited method with this method definition right here. So I can get my my use method doing this health potion specific thing, and then sword is just happy to take the default item use and take the method that was given by the game item class, and it's just happy to do that. I feel like I'm going to miss one thing, but I don't think so. Okay. Yeah, I don't think so. I got it all in my head. Okay, so we're going to override that code, and now when we call use from a health potion, we're going to get this overridden method. When we call use from a sword, we're going to get the default item used method inherited from game item. And let's set up some code to be able to use that. So let's create a new sword. Sword doesn't take any parameters. We gave it a default spawn and default attack power. We're going to use the potion. We're going to use the sword. Wow, I can't type. Use the sword. We already did move the potion. We don't have to do that again. And no, I'll do that in a second. And then let's run this code and see what we get. We're going to trace this code too, but let's run it first. So when we call use from potion, we get the potion use method. Notice that we don't get item used printed to the screen at all when we call use on the potion. And when we call use on the sword, that's all we get is item used. So the overridden method is going to be the one that's called. And I have this override annotation here, but this is actually optional. You don't need your override annotations. If I run this code again without that annotation, it'll do the same exact thing that it did before. So you don't need those. I like to have them, and I'm about to explain why with probably too much detail. The reason for the override annotation is to give the compiler a heads up that you're intending to override a method that you inherited from your superclass. So in this use method, if I have my override annotation, I'm giving Java a heads up and saying I am overriding a method that I inherited. And it'll make sure that you're actually overriding a method that you inherited. Yeah, scroll down when I ran. So it'll make sure you're actually overriding a method that you inherited. And it sees that you're inheriting a use method from the game item class, and it's checking the method signatures to make sure that it is an actual override. And as long as it is, the compiler is going to be happy and say, yep, you told me you were overriding a method, you overrode this method, everything's fine. But as long as, if you don't have the override annotation, As long as your method signatures match, so you have the same return type, name of your method, parameters, as long as everything matches, it will still override. So in the last example, I didn't say anything about override. Well, nothing was overridden. But when we go through our progressions, we're going to do it the same exact way that we did it on the previous example. And if we call use from a health potion, we look in the health potion class for a use method, we find it, we call it, and that's it. We only look in the superclass if we don't find the method. So when we call it from a sword, we don't find the method, then we go to the game item class and find the method here. But from a potion, even though potion did inherit this method right here, it's not going to be used because we overrode it here with or without the annotation. The reason for the annotation, so that's why this still used that potion health potion use method, because it found it here and then stopped the progressions, didn't look in game item at all. The reason for the annotation is if you make mistakes, like I do, like every human does, we make mistakes, and we want those mistakes to not become bugs in our code. So say I mistype this and I have a capital S here, or maybe I have a capital U. That might be a more common issue. A capital U here, I misspell this word, this method name. Now the method signatures do not match, and I am not overriding the use method anymore. And now when I run this code, I'm just going to get the default printed twice, the item use. So from a health potion, I call use, I look for a method named use, and I do not find it because I'm looking for lowercase u use, and I find uppercase u use. I don't find the method I'm looking for, so I continue my progressions to game item, find the use method here, and I call this one. So any small typo, if you're not using the annotation, any small typo is going to be a pretty big issue. You're not going to get any errors in your code, but your code isn't going to do what you expect it to do, and it's going to be a bug that might be a little bit tricky to find, especially if you're not writing all your unit tests like you should and everything. It's going to be a tough bug to find, and it could potentially be a bug that your end users find, which you never want. With our annotation, I get an error. Hey, you told me you were overriding something, but you're not overriding something. You look into this and figure out what you did wrong. So with the override annotation, I'm giving the compiler a heads up that I intend to override something. So if I don't actually override something, it's going to let me know. It's going to say, hey, not explicitly, but it's going to say, hey, something's wrong. Maybe you got a typo in your method name. And then I can see that error and say, oh shoot, yeah, I got a capital U here. And you can fix that bug before it ever becomes an actual issue. Without your override annotation, you better be perfect. If you're not perfect, you're going to have issues. With the override annotation, I'm allowed to make mistakes, and I'm going to find those mistakes because the compiler is going to flag me down and say, hey, you got something going on here. You told me you're overriding, but you didn't override anything. And I'm going to catch that mistake before it becomes a big problem. So I recommend, and I do use the override annotations just to make everything explicit, and also it makes your code easier to read. If I have this annotation, you know that I'm overriding a method. So you know to look for that if you're trying to understand what my code does. Without the annotation, harder to read, more error prone when you're writing it, just not a good idea. Unless you're a perfect developer and you never make mistakes, then go for it. Skip your override annotations. I mean, what are you gaining either? You just don't have to type these characters, I guess. You're going to spend way more time finding and fixing that bug than it will take you to write these annotations. I guarantee that. So I recommend it. Some of you will use them, some of them you won't. Some of you won't, but that's my spiel on the override annotation. I'll use that in examples, but I'll try to shut up for the most part about it. Moving forward. Okay, speaking of moving forward, let's move forward to the next thing. In my slides, I would do a trace right here, and then write the rest of the code, and then go to the slides, and then trace the rest. I'm going to do all the code now, and then do all the tracing, lump them together. So let's print some things to the screen. Let's print a potion to the screen. And let's print our sword to the screen. And let's see what we get. we're going to get this garbage. So this is the default, I shouldn't have closed it, object. So this is the default behavior of the toString method that we just saw. And even in the documentation itself, right here, am I blind? Oh, right here. Method that returns a string. Oh, I've been lecturing too long. Been lecturing since 8 a.m. What am I looking at? That returns a string. Am I just not seeing it, or did they actually remove it? I'd be sad if they removed it. Oh, right here. It is recommended that all subclasses override this method. So I say, this is almost always not what we want. I've never had a situation where this isn't what I want, so I might start saying this is always not what we want. Maybe if you just want to see the class name of your things. But there are better ways to do that. I would just run the debugger to find that out. And even the documentation, the official Java documentation, agrees with this. It says you should really override this method. It really only exists to be overridden, but they give us some default implementation just so the code will compile, just so you have a toString method. Because if you don't have a toString method by default, when you try to print something to the screen, it'll give you errors and stuff. It just says, we don't want to give you errors, so we'll give you something, but really just override this because what we're giving you is kind of meaningless. So we want to override this default implementation, and let's go to our game item class and override it. And the ID has us here. We just type toString. It'll give you the whole thing, the right syntax, but it must return a string and be called toString. Let me delete my annotation here and get rid of the default crap that it gave me here. And for a game item, I'm going to print its location in kind of the syntax that we expect from math class, plus this x location. So x comma y. If I can type, man, I'm struggling. Plus this dot y location plus a close paren. Really struggling. So we're going to print the location of the object. And now health potion, we look, when we call toString, we look for a toString method. We don't find one. We go to game item. We go to the game item class. We look for toString, and we do find this one. So we don't continue our progression to the object class. So we find this, and then this is the toString that's called. Same with sword. And if I do, just my last time talking about this, if I spell this wrong, I forget to capitalize my S. Now when we get to the game item class, we don't find a toString method. So we continue our progression to the object class, we find the default toString, and we're back to this default implementation of toString, which isn't what we want, which is why I would use the annotation. If I make a typo like that, it's going to yell at me. I'm going to stare at this a while and say, what is wrong with this? And eventually realize I have a lowercase s instead of a capital S, and write that toString. Now in sword, maybe I don't want that toString to be what I call. Maybe I don't want that toString. Maybe I want it to say attack power equals, let me put a space here, this dot attack power. Maybe I want that to be printed. Seems fine, seems reasonable. And then let's override it over here for health potion as well. So, and I'll type this manually. I feel like I'm abusing the autocomplete a bit much when I have it write a whole method for me. So let me just emphasize again. When you're using the autocomplete, it should be typing exactly what you would have typed. This is exactly what I would have typed, is toString. I just didn't feel like typing it out. But if it is typing literally character for character exactly what you were going to type, I shouldn't say literally because I didn't do this space. Usually the spaces, for what it's worth, is I'll do my auto formatter and it'll do all my spacing, get my spacing consistent. Auto formatters are a wonderful thing. You can write a little bit sloppy code and have it fix all your indentation, spacing, and all that stuff for you. Okay. And often when we override something, when we override a method, it's often the case that we don't want to completely override. Let me just get rid of sword completely here. We don't want to completely override this method, because a lot of times when we're extending a class, we're extending it because we want its state and behavior. We want the behavior from that class. So we want these methods to do the things that they're supposed to do. But sometimes we want to extend that functionality. We want to take the functionality that we inherit and then add our own extra stuff to it. And that's what we're going to do here. We're going to use the super keyword again. So aside from the super constructor calls, we can use the super keyword, which is in place of the super class name, game item in this case, and call the method that we're overriding. So we can call the toString method that we're overriding and then also add healing, potency. Let me just call it potency. Keep it simple. Potency equals this dot potency. So we're adding some health potion specific stuff to this method, but still keeping the super classes implementation for that method. So if we run this, we're going to get our weapon, our sword with the implementation that it overrode, and health potion is going to get the default implementation, not default, but the game items implementation plus some extra health potion specific stuff. So this is how we can expand on the functionality that we inherited. Instead of completely replacing it with an override, we're just going to take what we were given and then add to it. Okay, and now we're ready for a memory diagram. We're doing all right on time. I don't want to full screen yet. This is going to take a little bit of setup to get all of my stuff on here. Oops. And I closed my game item. Close my weapon class. So let's go grab that weapon, sword class. It's weapon in the... It's always weapon. It's always been weapon. I'm tripping myself up by changing it to sword here. But take my sword class, and the trick is getting this all on screen. So let's start erasing spaces. Erasing spaces between methods. Oops. The L is gone. Erase package declarations. Get rid of this, this. Oh my goodness. Somebody's running some type of machinery. For good measure, let's get rid of another override. That's fine. And I want to intentionally mix up the overrides when I am and am not using the override annotation to see the difference in our code. And spoilers, the difference in our code is going to be nothing. The override annotation does not affect how your code runs. It's only applicable during compile time. So when we're running the code, which is when you're doing the traces, when you're doing a trace, the override annotation has no effect on how that code runs at all. It's only a compile time thing, not a runtime thing. So the override annotations do not matter. I think that is a lawnmower. It's just it was so loud I thought it was something else. Somebody's just mowing their lawn. Hopefully it doesn't pick up on the mic, but hey, my audio sucks anyway on this mic, so what are we losing? Potion, maybe it'll make it sound better. New health potion. Which neighbor even is that? I got right up in the camera, didn't I? I think this is this neighbor over here who pays for a lawn care service. They're in and out quick, so I don't think it's gonna last long. If you can even hear it. It's probably just a distraction for me. You probably can't even, probably isn't even picked up on the mic, if I were to guess. Health potion. Map the constructor. We got this is OX100. Health potion has instance variable potency. It extends game item, which has X location, Y location. So we get those instance variables as well. X location, Y location. Then we're ready to call the constructor. X location, Y location are the parameters. X location, Y location, and we're feeding it 0.0 and 0.0. First thing the health potion constructor does is calls the superclass constructor. We have a second constructor helping us construct the same class. Super is game item, so we go to the game item class and call this constructor right here. So we have game item. This is still a reference to the object that's being created, OX100, and then X location, Y location are initialized. Oops, I forgot my parameters. Parameters X location, Y location. X location, Y location, which got X location, Y location from the health potion constructor stack frame, which are 0, 0, 0, 0. 0, 0, 0, 0. And then we can set them. This dot X location equals X location, 0, 0. This dot Y location equals Y location, 0, 0. This returns, gives control back to the health potion constructor, which initializes potency to 15. This dot potency equals a hard-coded 15. This returns and gives this reference OX100 to the object that was created to the main stack frame to the potion object, the potion variable. Next, we do something similar with sword. Sword, and the big thing here is don't forget your superclass constructor calls. Don't forget your return arrows. Like I just did. It's the biggest thing that I forget most often is my return arrows when I'm doing these. Let me not forget it here. New sword, I see the keyword new, so I know I'm hitting this button, creating a new sword. Sword, the sword class has attack power, extends game item, so I have to look at game item for the rest of the instance variables. X location, Y location. We got this as OX200, and then I'm ready to call the sword constructor. It takes no parameters, no arguments, so there's nothing in this stack frame. So many students, I mentioned this a bunch already, but so many students will fall into the trap of sword has 3 instance variables, so I need all those instance variables in the stack frame. It's not the case. This stack frame takes no parameters. This method call takes no parameters, so there's nothing except for this. We always have this in our non-static method calls, but we don't have any parameters, so nothing else goes in this stack frame. There's nothing else to put in there. If it's not, it's just like any other method call from 115 onward that you've ever done. The addition of this is different, but the parameter list goes in the stack frame. Parameter list is empty here. Nothing goes in the stack frame. I don't care that there's 3 instance variables. Instance variables pertain to the heap. Parameters pertain to the stack. So I got nothing else to put in this frame. Then it calls the superclass constructor, which is game item. This is still a reference to the object that's being created. And we're passing it two arguments, 10.0. I don't know what the parameters are yet because I didn't look at the code, but I know what the arguments are, is 10 and 4.5. I'm going to go to the superclass constructor, game item, this constructor right here. So the parameters are x location and y location. X location, y location. Actually, if this mic sounds crappy anyway, I can get it out of my way. I moved it because I thought it'd sound better if I was more directly head on to it. But if that ain't working for me, screw it. Alright, so we have our game item constructor, which is going to set the x location and y location. This dot x location equals x location 10.0. This dot y location equals y location 4.5. This returns, and I actually missed one thing. When we created the attack power instance variable, I haven't done this in a while in a trace, I missed it. When I initialize this, create this attack power instance variable on the heap, it is immediately initialized to 120 right in line. So when we create the object and add its instance variables, attack power immediately gets the value 120. And then sword constructor does not initialize attack power. It was already initialized in line right here. And then this returns a reference to the object that was created. And then this return. Okay. So that's our constructors. We've seen that already. Two more examples of it so we can make sure we see our superclass constructor calls in a little bit slightly different situations each time. Make sure you do not forget your superclass constructor calls. Don't forget your superclass constructor calls. Easiest way to fail the OOP quiz is forgetting your superclass constructor calls. Okay, then potion.use. The next thing that we need to worry about, which we did technically see in the first example, but it was impossible to get it wrong. But now use and toString, which is toString is implicitly called a print line. For these four method calls, we need to pay attention to which method is going to be called because we have multiple definitions of these methods. We have use right here. We have use right here. We have a lot of toStrings. We have 3 different toString methods being defined. We have to make sure we're keeping track of which method is called at which point in time. My video is recommended in Egypt. It's cool. Yeah, I hope they want to learn some computer science and inheritance in Egypt. So we're going to call the use method potion.use. Potion.use. We're going to call the use method from this object right here. Use, where this is OX100. And when we're looking for the method to be called, we do the same thing we've done the whole time, is we look at the type of the object that's calling the method. In this case, it's health potion. We look in the health potion class for a method named use. We find it right here, so this is the method that's going to be called. And I'm going to hide the IO a bit just because I want all the code to the screen. But what's printed to the screen is player was healed this dot potency 15 HP, which is the same as the previous trace. Nothing changed with this one. Can I get? Oh, it jumps way too far. I'm not in full screen. I do have a little extra space. Okay, we can get one IO line on the screen and all the code. Cool. And notice that health potion does inherit a use method from game item, but since when we went through our progressions, we started in the health potion class and we found a method named use, we never look at the game item class. We find the method to call right here, and that's it. We call that method, end of story. We only look in the superclass if we do not find the method, which might just happen pretty soon. Sword.use, we're going to call use from this object right here. So use, where this is OX200. That's an object of type sword, so we're going to look in the sword class for a use method. We do not find a use method. So only when we don't find a use method, that's when we're going to look at the super class. We go to the game item class, and then we continue our search for a use method. We find it in the super class, and that's the method that's going to be called. So we get item used when we call use from an object of type sword. It very much depends on the type of the calling object. Called through a health potion, we find use here, and we never look at the game item class. Called from an object of type sword, we do not find use, so we continue our search in the super class, and we find it here, and this is the method that's used. Okay, let's do the print line. So print line will implicitly call toString. So what we're going to trace here is potion.toString, sword.toString. In a memory diagram, I've said this before, but in a memory diagram, I would explicitly call toString if I wanted this as an example, as part of a trace. So it's not something you have to memorize, just because I've had too many little mistakes in the past, students failing quizzes who knew all the content. It was just kind of a BS question. So potion.toString. But for a lecture example, whatever. I'm having trouble getting everything on screen as it is. If I have two more lines to store the toString calls, I'm not going to do it. Potion.toString, so potion.toString, we're calling toString from this object, OX100. So toString, this, and the way I wrote this, we're actually starting with the trickier one, at OX100. So we're going to look in the health potion class for a toString method. We're going to find it right here, and it's this method that's going to be called. And when we call this method, to resolve all this stuff, we have this super.toString method call. So when we see a super method call, we're going to take super, that's in place of game item. So we're going to go to the game item class, since health potion extends game item, and look for a toString method here. We find it right here, so this is the method that's called from this call right here. So we're going to put another frame on the stack. We have another call to toString. And whenever we have a super method call like this, the keyword this is still a reference to the same object that called the original method. So it's still OX100. And then toString, we have a little bit of invisible code here. That's not going to show up in the trace. But this will resolve to the parentheses, all this stuff. And this is eventually printed to the screen. It's not captured in any variables, so there's a lot of invisible stuff in our trace. Again, in a tracing quiz, I would store a lot of these values in intermediate variables, just so they show up in your trace. For lecture, I'm just going to explain it verbally. So this is going to return whatever the super call returns. Since this is eventually being printed to the screen, I'm just going to start collecting our results on the I/O line. So we're going to get open paren this dot x location 00, comma this dot y location, this dot y location 00. 00, close parentheses. So that's the first thing that's going to be printed to the screen when we get the super.toString call. So that call's done, it's done its job, and then we have the rest of the string. Dash dash potency equal space this dot potency 15. So that's what's finally printed to the screen when we print a potion to the screen. So we got the super classes toString call, the one that we are currently overriding. And notice I don't have my override annotation here, but I do other places. At no point during this trace am I ever saying, look for the override annotation, or because this has an override annotation. No, it doesn't matter at all. The override annotation does not have any effect on your traces. If when you see the override annotations, you can just ignore them, or you can use those as a hint, as a reminder that something is being overridden. Doesn't matter if they're there or not. They don't change anything when it comes to overrides and which method is called. They do not affect anything. So we did get the method that we're overriding. We did call it still to extend its functionality and then added some more functionality onto it. And that returned and printed to the screen. And then we have sword.toString, sword.toString, calling it from OX200. So toString. This one's a lot simpler than the one we just did. This OX200, that's of type sword. So we look in the sword class for a toString method. We find it right here. And there's no super call or anything. We're just printing this to the screen directly. So let's get another IO line and print attack power equal this dot attack power 120. This returns. That's the end of the main method. That returns, and our program ends. And let's get all of the IO on screen, just so we can see it. That's our final trace. So don't forget your superclass constructor calls, and the method that's called depends on the type of the object first. And if we don't find the method there, we continue our progression to the superclass. Ooh. You go to, and if, by the way, if it's not in that superclass, then you look at that superclass as superclass and keep going until you find the method. If you don't find the method, something went horribly wrong because the code shouldn't have compiled. You shouldn't even be running the code to be able to figure out which method was called. The compiler should have found that and not compiled the code. Which, by the way, I haven't mentioned this yet, but here it is for the first time, is I'm not going to give you code on the quiz that doesn't compile. So you can assume that that's not going to be the case. Like, you will always find the method that's being called when you go through your progressions. Because I'm not going to give you a trick question, a trick quiz, where instead of going through the entire trace, the answer is this code doesn't compile. Like, I'm not going to do that. I'm not going to do that to you. Okay. Got everything. I don't think there's anything at the end of this lecture. Okay, we're ready for sorting. Let's do this. This one's going to be a little trickier to do live coding, but I ain't concerned. Okay. Actually, I'm not concerned at all. It's not going to be that tricky. So let's create a new class. In decreasing. Let's close all this other stuff. I closed my int decreasing class for some reason. Get rid of all of this because it's clutter. And what I want to do before we actually create int decreasing, I want to talk about comparators a little bit. So what we eventually want to do in this section of this lecture is sort. We want to be able to sort array lists. I mean, we'll use array lists as the example, but we want to be able to sort data structures. And to sort in programming, often, most of the time, most of this type of sorting we're going to do is comparator-based sorting, meaning that we're going to take a comparator that compares only two objects, two values, and then tells us which one of those two comes first. So in Java, and we have two different flavors of these comparators. One that returns an int, which is the one that Java uses internally, and one that returns a Boolean, and that's the style that we're going to write in this class. So let's just name this A. I'm going to give it a value of A. String A, string B equals B. So first I want to talk about the Java style comparator because it's going to be useful for your task 4, maybe a few other tasks, but definitely task 4, and explain what this comparator does. So if we have two strings, we can do one of our strings dot compare to another string, and that's going to tell us something about the relative sorted order of these two strings. And what it's going to do is give us a negative value if the calling object should come before the argument object. So here A should come before B, so it's going to give us a negative value as the return value of this method call. And it's going to have three different situations that it can return. If we swap the order of these, and if we have the same thing. So if the value that the object that's calling compare to comes strictly after the argument, what this is going to return is a positive integer. So we get +1 here. Any positive integer means that the argument comes before the calling object. Negative means the calling object comes before the argument, and 0 if their order is the same. So A compared to A is going to give us 0 because their relative order, their fully sorted order, doesn't matter. It's the same between them. And the way Java sorts strings is that every single, it does it mostly alphabetically, but with strings specifically, and this will come up in homework 4, in test 4, is that every single capital letter will come before every single lowercase letter. So we get a different value here for capital B versus A. So now A compared to B, it's giving us a positive value. That means that the argument comes first. So it's saying B comes before A, and that's because we have a capital B here and a lowercase a. When it's BA, it's saying capital B comes before A, and when we're comparing A to itself, it's still 0, of course. And these comparators, I keep saying positive int, negative int, and 0. Those are the values that it can return. Those are the types of values that it can return. So as long as this returns a positive int, it means the argument comes before the calling object. A lot of times these compare to methods will return 1, -1, and 0. Do not hard code that into your code. Do not say if compare to equal 1, if compare to equal -1, if compare to equal 0. Do not do that. You will get in trouble like this right here where we got 31 and -31. It's definitely not 1 and -1, but it is a positive int and a negative int. So your comparisons here are going to be, is it greater than 0, is it less than 0, or is it equal to 0? Those are the three conditions that you want to check. And this comes up in homework in test 4. So let's go to test 4 and talk about this really briefly, just a few things I want to highlight. Bayesian average, don't forget your edge cases is the only thing I really got to say about that. There are a lot of edge cases. When there are no valid ratings and you're asking it to add 0 extra ratings, I think I have them all covered in bullet points, but it's still the most common thing that I see in office hours on this assignment. Just don't forget your edge cases, or else you'll be bashing against the autograder saying you didn't test this feature. It's going to be the edge cases. But the one I want to highlight here is compare to ignore case. So with, actually right here I want to talk about it, is you're asked to write a song title comparator in task 4. And to do that, you can use this compare to method right here. Actually, I want to show an example of this in the code still. Compare to, ignore case in this situation, and that's going to return a positive int, a negative int, or 0. So make sure you're checking if this returns a positive int, a negative int, or 0, not +1, -1, because you will get errors if you're doing that. But often this will return -1 and +1, but not always. A lot of these. I think the string one rarely does, but other of them do -1, +1. So right here, you're going to want to call this comparator, and what you do with the return value is going to determine how well your code works. And we have this compare to This is the last thing I wanted to show with this example. We can do compare to ignore case because we often don't want this situation where it's saying capital B comes before lowercase a. We usually don't want to sort like that. What it's doing is sorting by ASCII value, and in ASCII, each character is represented as an integer, and the integers for the capital letters come before the integers for the lowercase letters. So everything capitalized will come first. Usually not what we want, so we have this handy compare to ignore case method, and that's going to get us back to where we want to be, back to telling us that A comes before B regardless of the capitalization. And that's what you're asked to do on task 4. And task 4, the utility method, also has you use compare to ignore case or equals ignore case, also exists. Equals ignore case is handy for the utility method. You can call this one as well, and which is a little simpler to work with since it returns a Boolean. You're not checking for 0. And oh, excuse me, it's hit me hard. I could get exhausted lecturing from 8 a.m. till 1:30. Okay, so you can do equals ignore case too, and with the testing utility method, it's specifically designed to not be able to just call assert equals on the two array lists. It's asking you to compare two array lists of strings for identical values, but you could ignore a case. So when you're doing that, you can use equals ignore case, but you do have to manually go through the array lists. You can't just let assert equals do all the work for you. That's why I'm ignoring case in that specifically, just so you get practice with going through array lists. When you're doing that, the first thing you want to do is check, whenever you're comparing two data structures like that, first thing you want to do is check if the two data structures have the same size. If they don't have the same size, then it's all over. Like, they're not the same. So the first thing you assert is that they're the same size, and then you want to go index by index. Are the values at index 0 the same? Are the values at index 1 the same? And you check each one with equals ignore case in the case of task 4. All right, so that's Java's flavor of comparators. We want to use a different flavor. I'm actually going to just straight up delete this. I'm going to delete this whole thing. I might bring my main method back, but what we want to do is switch to a style of comparators that's going to return a Boolean. Those are the style that we're going to write in this course. So I want to compare two ints. I'm just going to call them A and B. Matches the variables we just had with strings. A and B. And what I want to do is write a comparator that's going to sort my values in decreasing order. It's the simplest thing that we can do that's not the default sorting. So it motivates writing a comparator because we want to do some sort of custom sorting, but without getting bogged down in some complex comparator. So with this, I want to return A greater than B is going to be exactly what I want. Oh, I didn't even define my comparator yet. So when we return a Boolean, what we want to do is return true if the first argument comes before the second, and false otherwise, including ties. So if A comes before B, I want to return true. So if I'm sorting in decreasing order, if A is greater than B, then A has to come before B in that sorted order. If we use the less than operator here, we're going to get our default int increasing. It's going to sort your numbers in the way you would expect from grade school that would be sorted from 1, 2, 3, 4 in increasing order. So if we want the largest values to come first and sort in decreasing order, we're going to use the greater than operator. And strictly greater than, that's going to give us exactly our property of true if A comes before B, false otherwise, including ties. So if A and B are the same, this is still going to return false. And that's our comparator. Great. But we're here for inheritance. So let's talk about inheritance. We're going to create a new class. We're going to create a comparator class. And what I want is a generic comparator class that's going to define the compare method that's going to be overridden by the child classes. It's going to define this method, but it's going to work with any type. and I'm just going to return false here. So I'm going to write a comparator class that takes a type parameter, just like our linked lists, and we're going to take two values of that type, TA and TB. And then int increasing is going to extend comparator. And there's a special syntax, special thing when we extend a class that takes a type parameter, is when we extend the class, we can actually specify what that type parameter is. So I'm not just having int decreasing extend comparator, I'm having int decreasing extend comparator of integer. So I'm specifying what t should be, and then when I override my compare method, my types of my arguments, my parameters, need to match the type that I gave it here because they're both of type t. If t is integer, these need to be integer. And let's write a quick main method so I can show I definitely have a bug on screen right now. Int decreasing comp for comparator. I'm going to end up deleting this code anyway, so I'm not going to sweat too much about it. Comp of, oh my goodness, s out comp of, so we want to say does 5 come before 3 in sorted order? Comp dot compare, which should be true, right? 5 should come before 3. If we're sorting in decreasing order, since 5 is larger than 3, it should come before 3, and this should return true. And it did return true. I expected that to be broken. Okay, that's weird. Oh, I know why. So what we're going to do, what we're eventually leading up to, I have to foreshadow this a little sooner than I wanted to, is we're going to end up storing these int decreasing objects in variables of type comparator, which is actually allowed. This is something called polymorphism. We have a whole lecture on it in 2 weeks. We'll talk about it in depth when we get to that. But since int decreasing, the short answer of it is since int decreasing extends comparator of integer, we're allowed to store objects of type int decreasing in variables of type comparator of integer. So we get to start bending the rules about strong typing as long as the variable type is somewhere in the inheritance chain of the object type. Then we're allowed to mix types a little bit here. And this should return false. If this don't return false, I don't know what to do. Okay, it returns false. So when we call the method, we're getting the method call. We're calling this method from an object of type int decreasing. So we're going to start an int decreasing. We're going to look for a compare method that takes 2 ints, and we should find it right here and return true. But what's actually happening is we're going to, oh, this example is pretty confusing now. We're going to the comparator class and then finding this one that returns false. And the mistake here, the bug is, well, I like my override annotation. When we add our override annotation, it's going to tell us, hey, you're not overriding anything here. You're telling me you're overriding, but you're not overriding anything. What's going on? Fix your bug. And the reason is that these types don't match the type parameter. This method has to take values of type t, and I'm giving it some type that is not exactly equal to type t. Now, we might want to think, well, autoboxing is going to fix us here. Java is just going to convert my ints to integers and vice versa, so they're the same thing and everything's fine. But not in this case. You're not actually getting an override here because int is not the same as integer. So this is a case where we do need integer. Since integer is the type parameter, we need integer here. Our error goes away on the override, and our method is going to return true like we want it to. So this is a case where I really like my override annotation because that's an easy mistake to make, is putting int instead of integer. Very, very easy mistake to make. But the override annotation is going to flag me down and say, hey, fix your shit. Like, you got an issue here. Take a look into this because you're not going to get the behavior you want. And if your comparator just always returns false, probably not what you want. Alright, so we fixed that, and we got to talk about polymorphism ahead of time. And we have our comparator. A little bit of more foreshadowing. We're not going to get to this until the inheritance, the polymorphism lecture. It's an inheritance topic, but it's just there's just too much to cover in this lecture already. But eventually, we'll want this to be an interface and this to be an abstract method. It doesn't make sense to give this the default return false. We will fix that when we get to the polymorphism lecture. I just want to say this for anyone who knows about those topics already. Like, why is your comparator a class when it should be an interface? It's because I don't have time to talk about interfaces today. Otherwise, I would. Okay, so we have our comparator, and we can write, like, this is a simple comparator that we're writing today, but this can get a lot more complicated. Distance to player extends, what's the object that we have? Game item. Extends comparator of game item. So let's say that we have our game, and we want a comparator that's going to be used to sort game items based on their distance to the player. So we know we need to override the compare method. So let's override that thing. Override public Boolean compare two game items. I'll still call them A and B. Return something. And since comparators are classes, we have all the power that we have with any other class. So we can do all the regular class stuff that we can always do, meaning we can have an instance variable. If we're finding the distance to a player, we need a player object to be able to compare to. So we can have a player week 7. I'm just going to grab the player class, which is, oh, this player doesn't even have location. Forget you saw that. We're going to create a player class. This might be getting a little out of hand. What did I do in the slides? How did I get around this issue? Oh, I did write getters and setters. Oh no. I'm stuck. I gotta do this now. Let's do it. Let's do getters and setters for game item. Public double get x, return this dot x location. Oh no, is this even... This is just a side note. It's easy in the slides because I can just click one button and all the code is just there. I'm committed at this point though. So we're going to add our getters so we can get x and y outside of the game item class. Player is going to extend game item. Doesn't fully make sense for a player to be a game item, but that's my quickest way to give my player location information. So public player double x double y super xy. There's my player. So now I can have my instance variable private player. I want to get rid of this unused import. Make sure I get the right player object. Private player and a constructor to initialize the player. Public distance. Oh my goodness. I'm panicking. Distance to player. I just don't want to get off on time now. Distance to player is going to take a player object. I'm not going to run this code for what it's worth, just because that would take even more time. This dot player equals player, but I want to at least set it up and show you all the stuff that we can do. And then we can write a method. We can write helper methods in here. So we have constructors, instance variables, methods. We can do all of this stuff. As long as we override compare, we can have anything else in this class as well. We can do all kinds of other stuff, all of our class stuff that we know how to do. As long as we do have that compare method, that's the only requirement to make this a comparator. So private, I'm going to have a way to calculate distance. Call it distance to player even. Takes a... Actually, I only need this to take a game item. Takes a game item, and then I want to compute the distance between that item and the player. Okay, and I'm going to do this in one line. Math dot square root. I'm going to compute the Euclidean distance. That's the square root of the sum of the squares. Math dot pow sum of the squares of the differences. So we're going to have the square root of the sum of the squares of the differences of the locations of these items. So this dot player dot get x minus item dot get x, and I don't care if it's negative because it's going to be squared. And I'm going to copy this in the interest of time, paste it here, place the x's with y's. It's a beast of a line. Let's break that up. Probably the most legible way to break it up. And then I want the closest item to be first. So distance, this dot, distance to player of A less than, so I'm sorting in increasing order, distance, this dot, distance to player. This is definitely optional in these method calls, but I like it because it makes my code more explicit. And then this comparator is going to sort items based on their distance to the player, which is something you might want to do in your game. You want all of the closest items first. Maybe you have something that's checking the closest item with certain properties, the closest interactable item maybe, and you want to sort and then go through that list to find the closest interactable item to the player. And then if it's within range of the player, that's the item that they're going to interact with on that frame. So there's a lot of stuff we can do with comparators. This, I don't know if this example is worth it, but just to show you that these comparators are going to get can get more complex. They won't in 116, but you can do all kinds of stuff with these comparators. But for the sake of example, we're going back to our basic greater than operator and just sorting integers in decreasing order. But we do have lots of power with these comparators. So we can compare anything, because we're taking a type parameter, we can sort anything, and then we're writing custom comparators so we can sort them in any way. That's the amount of flexibility we want. So when we're writing our sorting methods, we're going to use a comparator to be able to sort anything in any way, complete custom sorting, while at the same time only writing our sorting algorithm one time. So with that, let's write our sorting algorithm itself. So let's create another class. I'm just going to call it sorter. I think that's what I called it before too. I don't even see it. Oh, I call it insertion sort. Sorter, and I want to sort these values. This is going to be an insertion sort implementation, meaning if we have some input list, I'm going to use the same list I have in the slides, just because I know it's going to do one certain thing that I want it to do. what this means is that when we have some input list, we're going to go through the input list one at a time. So we're going to start with 1, and we're going to find where that belongs in the output list, which will be fully sorted. For the first value, there's no decision to be made. We're just going to copy it over. For the second value, what we're going to do, the way I'm going to write the code, is we're going to check if we're going to count how many values in the output come before this value. So when we're comparing 6, we're going to ask, does 1 come before 6? And we're going to use our comparator to do that. We're going to say compare 1 to 6. Our comparator in this case is going to be our int increasing, or int decreasing. Let's get this on screen. Our int decreasing comparator. So we're going to say, and we don't need this anymore. So we're going to say, is A greater than B? Is 1 greater than 6? False. So we counted a total of 0 values in the output that come before the value that we're adding, which means we're going to add that value at index 0. So 6 comes before 1, and 1 gets pushed down the list. When we get to 5, we're going to go through all the values in the output. We're going to say, does 6 come before 5? Yes, because 6 is greater than 5. Does 1 come before 5? No, because 1 is not greater than 5. So we found one value in the output that comes before the value we're inserting, which means we're going to insert 5 at index 1. So we're going to insert 5 right here and push 1 down the list by a little bit more. And this is our final fully sorted list in decreasing order because we used greater than. If we used less than, we would get exactly the opposite. We get 156. So that's the method that we want to write. That's what we want to implement in this code. So let's do some setup. We're going to have a instance variable. We want to have a comparator in this algorithm. So we want some comparator. So let's store that as an instance variable. Comparator of t, which I'll call comparator. Because what else would I call it? And since we have a type parameter, we're going to need our class to define a type parameter t. And I'll have a constructor, public sorter, which is going to take that comparator of t and initialize my instance variable. So we're taking we're sorting something of type t. We're going to take a comparator of type t and store it in an instance variable so we have access to that comparator whenever we need it. And then the method we actually want, the method that actually sorts, I'm going to take an array list. I'm going to return an array list. That's not the takes yet. I'm going to write a method named sort, because what else would I call it? Sort, that's going to take an array list of t, my input, and it's going to return an array list of t. My array list of t output equals new array list. It's initially empty, and eventually I'm going to return this array list. Before we do that, I want to write a main method and set up my example that we just did on the that we did right here. I'm going to set this up as an example. So I'm going to say sorter of integer sorter equals new sorter of new int decreasing. So I'm going to create a comparator, int decreasing, and I'm going to feed that into the constructor of sorter as the comparator. Now, just like we already saw this, but int decreasing, an object of type int decreasing can be stored in a variable of type comparator of integer because it is a comparator of integer. And for this specific sorter, t is integer, so this is a valid call to the constructor since int decreasing matches the type because int decreasing extends comparator of integer. So we do get away with that one. That one works. It's via polymorphism. It's a magic that I'll have a whole lecture to fully do justice to. Then I want an array list. I'll call input. I'm going to reuse the variable input. I can do that because it's in different stack frames. Equals new array list arrays dot as list 165. Whoa, back up there. Holy crap, I'm missing some things. Array list of integer. Completely forgot my type parameter. Array list of integer output equals sorter dot sort. Oh man. Input. Then just for good measure, we're going to print output to the screen. So if we run this, we'll get empty string, or not empty string, empty array list. So let's implement our sorting method and make sure we get 651 as our actual output. I'm going to implement this. When I walk through this example, I did it in exactly the way that I'm going to write the code. So let's write the code that matches how I explained that one. So let's do it. So I'm going to count for each. I'm going to use a for each loop. Value from input as an int. Oh, not as an int, as a t. Goodness gracious. As a t. Now notice we don't know what t is. All we know is that we have an array list of t's and a way to compare t's. So we're just going to use this comparator to have all of the actual context of what we're sorting, and our algorithm needs to be completely generic. It needs to be able to work with any type, with any comparator, and we can do that by using a comparator of type t, by combining a type parameter and a comparator object. We're not hard coding anything, and this sorting algorithm can be reused any type, any comparator, anything, anywhere. So let's iterate over the input. So for each value in the input, we want to find where it belongs in the output. So I'm going to initialize index to insert equals 0. So I'm initially going to just by default insert at index 0, but I want to iterate over all the values, value from output in output. If this dot comparator dot compare, if it says the value from the output comes before the value from the input, then I want to increment my index by 1. Once I'm done with this loop, I went through everything in the output. Why is it complaining here? It's always empty. Yeah. After I've gone through every value in the output and I've counted how many values from the output come before this value from the input that I'm inserting, after that loop ends, I can insert into output.add, and I'm going to use our second add method, the one that takes an index and the element to add, and I'm going to specify the index to insert. So insert at this index the value from the input that I'm inserting. And that's our sorting algorithm. 651 looks good to me. It's only one test case. I would have to do thorough testing to make sure I did this right, but trust me, bro, it's right. So in 12 minutes, we want to trace this thing. Trash can that, full screen this, get rid of all this code, back to IntelliJ. I need int decreasing, and I need comparator. Why is there oh, I literally cut that instead of copied. And comparator. Okay. Let's make sure nothing's on fire. Okay. Alright, and we're only going to need one I/O line. Confident we can get all this crunched in. Let's get rid of this. Oh, we're already there. Yeah, let's leave that on there, actually. Okay, let's go through this. So we start the main method. We're creating sorter. But we have quite a bit of work to do before we can even call this constructor, because we have a constructor call inside a constructor call. We have to resolve what's inside the parentheses first. So let's create a new int decreasing. So let's do int decreasing constructor, where this is going to be something. We have the keyword new, so we know we're hitting this button right here, and we're creating a new int decreasing. Map the constructor. Int decreasing, look for all the instance variables. There are none. Go to the superclass comparator, look for all the instance variables. There are none. So we actually have no instance variables in this object, which is something we're allowed to do. It's usually an indicator that we could use static methods, but actually we would still want to use objects in this case because we're using comparators. And we want those to be objects. This we rolled OX100, and we got a lot of hidden code here. I wouldn't do this, again, another thing that I wouldn't do on a quiz, but in lecture example, it gives me more stuff to show you, hopefully give you a better, more well-rounded understanding of everything, is int decreasing doesn't have a constructor. If you don't have a constructor, you get the default constructor. We did talk about that before, so I'm still getting a constructor call. Every class has a constructor, at least one constructor. So I still have a constructor. It's the default constructor. It's public. It takes no parameters, and it has no code in the body explicitly. But what it still does have, because what always, 100% of the time always happens, is it still calls the superclass constructor. So we do still get comparator, comparator. We still get the comparator super constructor called. This is still a reference to the object that's being created. It's still called. It also is implicit. There is a superclass constructor here that's implicit. We didn't write a constructor, so we get the superclass constructor, which does in fact call the object superconstructor, but the object constructor, it happens all the time, but it's internal to Java, so we don't bother tracing it. So this constructor does nothing. This constructor called the superclass constructor, but doesn't do anything else. And we get this right here resolving to the reference OX100, which we can feed into the sorter constructor. So we have sorter. I don't know why I just want to do sorted. This is going to be a reference to the object being created. We see the keyword new, so we know we're hitting this button right here. We have a new sorter object mapped to the red constructor. Sorter has one instance variable comparator. So we have comparator. We have this. We rolled OX200. We took one constructor parameter, which also is called comparator, which is why I copied it here, which got that reference OX100 from this constructor call. So we fed that right into the argument list of this second constructor call. And then this constructor, this dot comparator equals comparator, which is OX100. And there's no superclass. Technically, the superclass is object, but we don't trace that because it's internal to Java. So this returns, I forgot my return arrow, it returns OX200 to sorter. Next, we're creating an array list. We've done this plenty of times before, but now with more context, it's more of a trap because it's easy to possibly overthink this. But we have new array list, so we know we're clicking this button and creating an array list. That much we can get right away. But since array list and this as list static method call, since these are both internal to Java, we don't actually trace anything. We just have to know that an array list is going to be created. There's no constructor to map. And we have to know what arrays.asList does. It's going to put 165 at indices 0, 1, 2. And that's going to return this reference OX300 over here. And now we get to the line that we're here for, sorter.sort, because all that's review. This object right here is calling sort. So sort from OX200. Input is OX300, so I know I have an argument, OX300. I don't know what the parameter is yet. Sorter is type sorter. Sorter, looking for a sort method, it's right here. And the parameter is called input. Then we trace through this code. Output equals new array list. So that means I'm clicking this button, new array list with nothing in it. Not initialized to anything, and output gets OX400. And we're going to hit a code block. This code block does have a variable created in it, so I do need to trace my code block. Value from input, which is going to iterate over the values of the input array list. So input is OX300. We're going to iterate over 165. So this is initially 1. And then we're going to get to this inner loop. This inner loop is going to iterate over output. Output is empty right now. Output is an empty array list. So this loop actually doesn't execute at all. It doesn't do anything. We just skip right over it and go into output.add. So output.add index to insert. Oops, I skipped index to insert. Index to insert is 0. So add at index to insert, which is 0. So at index 0, we're going to add the value from input, which is 1. We hit the end of the loop. So we update value from input is going to be the next value, which is 6. So this updates to 6. We actually redeclare this variable. This variable technically is destroyed at the end of the loop, and then we redeclare a new variable. We're not going to capture all that in our traces. We're going to cross it out and just pretend that we're reassigning a value to the same variable. Just keep things simpler. It's such a nuanced point anyway. It's not going to affect the way your code runs, but how it's represented in memory a little bit. So we're just going to pretend it's reassigned. Then we get to this output loop. This time this does execute, so we need a code block in a code block. You can never have a stack frame inside a stack frame, but you can have a code block inside a code block. And we have value from output, which is going to iterate over all the values from the output. It's just 1, so we're only going to get one iteration of this loop. Then we get to this line right here, this.comparator.compare. We have a method call this.comparator.compare. So this comparator, this int decreasing, is getting this compare call. So we have compare, where this is OX100. We're getting value from output. Value from output is 1. Value from input is 6. I thought I clicked that twice. Is 6. And when we go to the int decreasing class, int decreasing, notice we're not going to comparator, we're going after the type of the object. Int decreasing, we find compare right here. This is the method that's called. We have parameters A and B. A and B, and we're going to return A greater than B. A greater than B, that's false. 1 greater than 6 is false. So this is going to return false, meaning we are not incrementing the index. And then that's the end of this loop. And then we're going to call output.add. Output.add at index 0, the value 6. So at index 0, we're adding the value 6. And when we added an index, we put that value at that index, and then whatever was there and beyond is going to get pushed down the array list. So we're not overwriting. We're not just setting the value at that index. We're adding the value at the index and then preserving everything that was there, albeit at different locations than they were. Okay, then we get to the front of our input again. So this is updated to 5. We're on our last value from the input array list. Index to insert gets reassigned 0 again, technically redeclared. Then we hit our inner loop again. For a second time, value from output. Output, the first value is 6, so this is going to get the value 6. Then we're going to hit our conditional again. So we have compare. This is OX100. A, B, value from output is 6. Value from input is 5. This comparator is going to return 6 greater than 5 is true. So this time we are incrementing our index to insert up to 1. We're going to the beginning of this loop. Value from output is going to be 1. Then we're going to call our comparator again. So even though our comparator can only compare 2 values, since we're calling it multiple times, we're using this one comparator to compare an entire array list of values. It's only 3 in this example because I want to keep the trace somewhat short. But if this were 100 values, we're just going to keep calling compare a whole bunch of times. 1 less than 5 is false, so this returns false, and we do not increment index to insert again. That's the end of this loop. So we're adding index to insert 1, the value 5. So at index 1, we're adding the value 5 and then sliding that value 1 down the array list again. That's the end of this loop. Then we're returning output, and I forgot my return arrow again. Oh, I didn't even put output on the stack. Output. And then we return output OX400. And we print it to the screen. 651. Then the main method ends. Okay, I got a little overconfident there because we actually ended the 8 a.m. lecture early, so we went 1 minute over, probably because I was messing with my mic so much. Stupid mic. But that's lecture. If you're coming to office hours, I'll see you then. Otherwise, I will see you next Tuesday. Good luck on task 4, everybody. Aim for that expected deadline. Don't let this one trip you up. Take care. See you on Tuesday. See you, Thickless.